right, so yesterday I posted another assignment on Canvas, which is the Excel assignment. So we'll have kind of these two assignments kind of running side by side. The Excel goes a little bit further than the Connect does, so kind of dates basically from today. So I would start with the Connect and work on that. For right now, part of the Excel that you can do is probably just like the very first kind of set of questions. You can have it broken down to like 3 different kind of set of questions. The only thing that we've worked through is that first set, so you can get started on it, but we won't kind of address the other stuff. So probably next week, we might just touch on it on Friday, but for the most part, we'll be covering the rest of what's on that Excel assignment next week. Okay, but the Connect assignment, you should be able to make it pretty far into that, up to kind of where we're at now. We kind of got them up a little early so you can kind of work on them as we go along. Okay. We should have kind of this week's lectures. I've kind of moved all the old stuff, the old lecture slides. If you ever want to go back, all those old kind of PowerPoints and PDFs are in there. Other than that, any questions from me before we kind of get started? Hopefully we had a good fall break. We're kind of rejuvenated. So we left off kind of talking about, normally distributed variables. We started to say, okay, if I have a normally distributed variable, I need to convert it into a standard normal distribution. So I can then use that table to find the probability of being above a value, below, between. So I think we had just worked through some examples where we looked at how do we find the probability of being below a certain value. Those are kind of easy because that's what the table tells us, right? The table gives us this cumulative probability, or visually think about it as the area to the left. We then to go look at how we do that in Excel, kind of using that norm.dist or that norm.s.dist function. We might kind of revisit that here today. We'll do a little bit more work in Excel once we start to talk about something else, which is called the inverse. But before we get there, just kind of refresh our memory where we're at and kind of work through an example like where we left off together. So we're looking at rainfall and temperature, and pretty close to a normal distribution, right? So we have June temperature. So if we look across time, it looks pretty normally distributed. We're told that it has a mean of 70.75 and a variance of 6.3. What's the probability that we see this June that temperature is greater than 71.4? So anytime we start working with this normal distribution, I think it's really helps clarify a lot of things if you just draw it out, right? Because there's a couple answers up here that we can definitely rule out just from the visual. We started off with this variable x, which is what, temperature. We know that it's normally distributed. It had a mean of 70.75, and the variance is 6.3. So we don't always do this, but sometimes it helps to kind of think about how many standard deviations away from the mean that we are. So I just grabbed this marker. So let me get this and show you. We want the probability of seeing something, or seeing the temperature be 71.4 or greater. And I know I put the 71.4 there because it's to the right of that mean, right? It's a greater value. Well, to kind of help clarify, if you just want to find the standard deviation, what would that be here? Just the square root of variance, right? So the square root of 6.3. If someone wants to help me out, what is that about? Approximately 2.5? 2.5 now. We'll get the idea. Okay. Thank you. So we've got about 2.5 as our standard deviation. So what we want to do is turn this cutoff value 71.4 into a z-score. But if we remember that z-scores reflect the number of standard deviations away from the mean that we are, well, if I'm looking at this one, I'm not even 1 unit, right, or 1 degree away from that mean. If my standard deviation is about 2.5, I'm not even a half of a standard deviation away from that mean. Okay? Like I said, as we work through more examples, we'll become more familiar, but we said last week that 2 or 3 standard deviations is very far from the mean. But not even half a standard deviation, right? We're starting to get that we're not very far from that mean. So our z-score is going to be relatively low. So if I think about if I have a relatively low z-score, or a z-score that's getting close to 0, being 0 standard deviations away from the mean, the area to the right of it should be fairly close to what value? So remember, if I turn the mean into a z-score, it's going to have a z-score of what? How many standard deviations away from the mean is the mean? 0, right? So that mean will always have a z-score of 0, which said the area to the right and left of the mean is going to be pretty close, or sorry, not pretty close. The area to the left and the right of the mean will be 0.5. So if I'm getting a z-score, and I might have drawn this a little bit of out of proportion here, but I just said my z-score, I'm less than a half standard deviation. I'm going to have a z-score pretty close to 0. So the area to the right of my z-score is going to be pretty close to 0.5. Or at least closer to 0.5 than it would be to, I've added 5 standard deviations away from the mean. The area to the right of that is going to be pretty close to 0. So if I'm looking at these answers, let me know if stuff like that happens. And realize that popped up. Right. So if I'm looking at these answers, well, right away, I know this area has to be less than 0.5, but it might be close to it. It's less than. So I can rule out B and C right away. And if I'm choosing between A and D, well, I just said I'm going to have a z-score pretty close to 0, so the area to the right of my z-score should be pretty close to 0.5 or closer to 0.5 than it would be 0. So if I'm going to guess between A and D here, I'm probably thinking A is probably the right answer. But if I want to actually work through this, I can turn that value 71.4 into a z-score by taking that value, subtracting the mean, and then dividing by that standard deviation. Since I think I wrote it down incorrectly, instead of writing the actual value, I don't have to do this in steps. I could just plug in the square root of 6.3 there in the denominator, right? Because I know that represents the standard deviation. That was just our equation for the z-score. Right, which was take the difference between the value you're interested in and the mean, and then divide by the standard deviation. So if I do that here, I probably get something pretty close to 0.25. So yeah, 0.259 is the z-score that I come up with. Okay? So I'm about a fourth of a standard deviation away. How do I find this exact value? Well, at this point, I've got a z-score, so, whoops. I'm going to go to the tables. Scroll down here. Now 0.259, I can only look things up to the second decimal. So I'm going to have to round my z-score always to the second decimal. So here, 0.259, we'll use 0.26. So 0.26, the area to the left is 0.6026. So when I look that up, remember the table gives me the area to the left. I wanted the area to the right. So what's the other step that I have to add in now? I want to find the area to the right. The area to the left is 0.6. The area under the curve is 1.
1 minus 1.
Yeah, just 1 minus 0.6026, which gives us that 0.39, right? 0.397. Questions how I work through that one? All right, so I know I had this pulled up, but then I think I didn't start it. So for following along with that, just kind of let me see where we're at with doing these on our own. And hopefully by this point, you have some way either printed out or pulled up on your phone or on kind of a computer, that Z table, that standard normal table. So the next one, oops, some of you got a little bit of a help there. Now this one should be relatively easy. In fact, I wouldn't even have to go through the entire process if I didn't want to. If I was to kind of draw this out, I come up with the answer that we pretty quick. So let's say we're now looking at February temperature, assuming that it has a normal distribution, a mean of 28.89, a variance of what, 26. And I want to know what's the probability that in 2017 we saw the average temperature in February be 42.85 or greater. All right. So very similar to the last problem that we did. I guess I hope maybe drawing this one out to actually avoid even having to work through, solve, and calculate the z-score. But I recommend trying to work this one out all the way by hand, even if you can rule out a lot of the answers here and get to the correct one. So give you a little bit of time working on it, talk to the people around you, and we'll kind of come together and talk about it as well. Looking for the probability it's greater than 42.85. Go to that 3:30 mark, so another 30 seconds or so. All right, so if you haven't got an answer in, let's take our best guess here. Thought I counted 30 people, but make sure you get your answer. I'm going to close it out here. That's for 30 of us. All right, there you go. Okay, close this one out. 31. Last call. All right, close it out. So let's just draw this one out. So I have this normally distributed variable. It's got a mean of what? 28 approximately. Mean 28.89. Variance is 26.16. So just to kind of give you some context, my standard deviation would be square root of 26.16, which I know is 5 point something small, 0.11. So I've got a much larger standard deviation here, right? So when I see values that are far away from the mean, well, they might be far in number of units, but maybe not in the number of standard deviations. For example, here, let's say I was thinking about, instead of this value of 42, what if I was thinking about the value of, I don't know, 35? Well, 35 would be 5 degrees away from the mean, right? That's how many units away it is. But if the standard deviation is 5, it's only going to be 1 standard deviation away. Right? So because our standard deviation is larger, seeing something a higher number of units away doesn't necessarily mean that it's a large number of standard deviations away. Especially if you imagine we had a variance of like 30, right? Well, then seeing something 10 away is not even a third of a standard deviation. So we're thinking about this value of 42.85. If I'm just roughly looking at this, it's more than 2 standard deviations away, right? It's more than 10 away from that mean. So I'm already thinking it's about 2, it's going to be more than 2 standard deviations away. That's starting to get pretty far, right? So right away, right, what do I know this probability is going to be pretty close to? If once I turn this into a z-score, I just said, just by eyeballing kind of value, it's more than 2 standard deviations away. So even if I think about that z value being 2, which I think is actually quite a bit higher, but I'm really rounding really inappropriately here, just to get the idea across. The area to the right of the mean is 0.5. So right away, I know the area that I'm looking for is going to be less than 0.5. Not only is it less than 0.5, once I get to like 2 standard deviations away, that area starts to get pretty close to 0. So if I'm looking at these answers, just based off of what I've drawn here, what has to be the correct answer? B, right? It's the only thing that's less than 0.5. In fact, A doesn't make any sense. I'm looking for a probability. It has to be between 0 and 1. But I can work through this, right? So I'm going to calculate that z-score by taking my x value, 42.85, subtracting that mean, and dividing by my standard deviation. If I do that, my guess is I get a z value of 2.73. Guess that's why it's right up there. So 2.73. I can look that value up in the table, and it'll give me the area to the left of that. So if I look that value up in the table, right, go to 2.7, then go over to the 0.03 column, what value do I get? 0.9967. Hold on, I don't think that's right. It's up, right? So it might just be kind of switching 6.8, yeah. So one thing with this table, if I'm doing this by hand, it's helpful to have another piece of paper. I do this all the time when I'm looking at it. Accidentally, my eyes go down a row, and I don't realize that it does, right? So if I'm looking at this, and I think, okay, here's 2.7, I start going over, and I kind of lose track, and I might accidentally fall to the next row without realizing now I'm at 2.8. So 2.73. So I'm in this column, all the way down to 0.9968, right? So 0.9968. Oh, kind of work to do this. But then I have one more step, right? Because the table always gives me the area to the left. If I had this drawn out, I even remember, oh yeah, I wanted the area to the right. So I have to subtract that from 1. Any questions over anything in this process? Starting to get a little more comfortable, kind of hopefully using this z table, looking up different z values, finding the area to the left. Sometimes you have a little more work to do. Subtract it from 1 if you want the area to the right. Eventually, we'll start working through some examples as we transition probably between 2 values. Right? We've already done this in the past, right? We already did this with just the z values. I'm just saying that once we convert a normal distribution to a standard normal, we also know that if we were wanting to find the probability being between 2 values, we just look up the probability being lower than the lower z value, subtract that from the probability being lower than the higher z value. Questions on this? I think we even did this in Excel last week, where I show you, you use that norm.dist, and then if you want the area to the right, just subtract it from 1. Hopefully we're feeling all right with these, or at least remembering it's all coming back to us, hopefully. So chose this example because it was really interesting, and I kept it in there because this was actually the real numbers. So back in 2017, before any of you guys were here, well, maybe some of you were, I don't know, but hopefully not. So, we saw the average temperature be 42.5. So what was the likelihood of seeing it be that warm? It's actually about a 0.32% chance, right? Based off of the historical data. So I don't know, you could do things like this, kind of interesting. These weather examples are a little bit trivial. I say trivial though, but depending on what industry you're in, the probability of seeing temperatures be this high in February might greatly affect your business, right? So you can see how that might be. So everything that we've done, we've started out with an X value, then turned it into a Z-score, found out how many standard deviations away from the mean was, and then we found the probability that we saw something that many standard deviations away. What we might want to do is work backwards. So what we might want to do is we might say, okay, look, I'm interested in what value, I can think about maybe even using like height or something. What value for height would give me the 90th percent cutoff? Right? So what value for height would there be? 90% of people would be below that height, and I said differently, right? 10% of people would be above that. So what is that height value? What's that cutoff value? Well, because I know the probability that I'm interested in, right, I can think about there is some value where I could in the table look at those values in the middle. Remember, those all represented probabilities. So if I can look at all those probabilities and find 0.9, well, then I can go over to the column heading, or sorry, over to the row heading, up to the column heading, and figure out what Z-score would give me 0.9 below it, or what Z-score has a cumulative probability of 0.9. So I'm kind of working reverse. Before I was using the row and column heading, right, to look up the Z-score I calculated, and then finding the area in the middle that represented the probability of seeing that Z-score anything to the left. Now I'm going to go into the middle of the table first, because I know the probability I want, and then go over to find the corresponding Z-score. Now, once I have that Z-score, if I think about my Z-score equation, well, now I would have this value. I could figure out the mean and the standard deviation of my original value, and then I could kind of back out what this cutoff value X is that would give me that Z-score, which I know corresponds to the probability that I originally wanted, right? 0.9. Or I was saying like 90%. So if I just rearrange this a little bit with algebra, I end up with this. So if I want to work in reverse or the inverse transformation, I use this formula to find my cutoffs. So that's the conceptual idea behind what we're doing. I'll kind of walk us through an example in a second. So, I rearrange this equation. We've got our inverse transformation formula. So now I can work in reverse. So I think I have an example here. Oh, there we go. So I'm going to use this same idea. What cutoff, right? What was the cutoff for the top 10%? Or said differently, the bottom 90. If I've got a test score that's normally distributed, I know that that test is normally distributed around the mean of 72. The variance is 64, which means my standard deviation is what? The square root of 64, so 8. And I want this exam score such that it would be better than 90% of the other scores, right? Right, if it's the cutoff for the top 10%, that would mean that there would be 90% below. So the exact same setup as I kind of had in my original example. So what I'm going to want to do is first find that Z-score that corresponds to having an area of 0.9 to the left of it. So I go to my table, and I'll kind of show you how we use this table in reverse. So I no longer am looking up a Z value. I'm looking up the probability I want. So I'm going to look through all these values and find the value that's closest to 0.9. Okay. So I'm looking through here. This is getting pretty close. Go over here. This is really close. This is close as well. Notice I can't get exactly 0.9, but I can figure out, right, what two Z values would be between. Now, if I was doing the actual versus looking at the actual integration where I could use any decimal I want, we could come up with an exact z value. We'll actually see how we could do that in Excel. I could use that norm.s.dist function to find that exact kind of probability of 0.9. But if we're doing this by hand, kind of the method we'll use is, okay, I find the two probabilities that are closest, and those correspond to z-scores of what? 1.2, and I scroll up, 1.28 and 1.29. And if I'm in between two values, I'll always just take the higher of the two, or the greater and absolute. I'll take, if I think of the absolute value, so if they happen to be negative, I kind of ignore the negative sign. So I take the larger and absolute value, or the one that has the highest magnitude. Right? So in between 1.28 and 1.29, I'll use 1.29 there. Okay. Well, now I've got everything I need. I've got that inverse transformation formula over there. I've got my z-score, I've got my standard deviation, I've got my mean. Now it's just a matter of plugging everything in. So, right, we looked up kind of that z-score. The one that we can get closest to 0.9 was at 1.29. Now it's just a matter of plugging all of our values in. Okay. So this would tell me that for this specific exam, an 82.34 was kind of that 90% cutoff, right? So this is what we just found. Okay. Any questions on this process, kind of working in reverse here? So I think I have another one. And I'll just kind of talk through this one with you. So let's say I have the same kind of setup, but now I want to know what would the cutoff be for the bottom 40%. I don't know why the hell I want this, but it presents something that we might run into that is kind of difficult. So I'm not going to say difficult, just we should be aware. I've got the same setup, right? My mean's the same standard deviation. I want the value that's going to be the cutoff for the bottom 40%. Right away, I know this value has to be less than what? What does this value have to be less than? At 72, right? Because the area to the left of 72 is 0.5. I want an area of 0.4, so I know that I'm going to be looking at a value that's below the mean. So when I look up the z-score, I should be finding a z-score that is what? Positive and negative. Negative, right? It's below the mean. I know the z-score will be negative. That's all I know. I don't know anything else about it. I know that it's going to be negative. So I'll use my table to find that z-score that gives me an area of 0.9 to the left of it. Sorry, 0.9. That was the previous one. 0.4 to the left of it. So I go here. I'm going to find what's closest to 0.4. Looks like I'm in between these two values. So negative 0.2, scroll up. Negative 0.25 and negative 0.26. I'll use the higher in absolute value with a larger magnitude, so 0.26, negative 0.26. Now that I've got negative 0.26, it's just a matter of kind of plugging in, plugging our z-score. Here was our standard deviation. Here was our mean. All right. This is a different way of thinking about it. If you wanted to, you could have used the z-score formula, plugged everything in, and then just did the algebra to solve for that one thing you didn't know. Or we could rearrange that equation first and then plug everything. I think that's probably the easier way to do it, is to rearrange the equation first, just use that inverse transformation formula. But I just want to show you can put everything into the z-score formula and then just do the algebra after that. So here I've got what, 72. This is where I have to be careful. I found that z-score of negative 0.26. So when I plug this in here, I need to make sure that I can keep that negative sign. Otherwise, I'll end up with a value that is above the mean, which I know that should not be the case for what I'm looking for. And then I did the intermediate calculation ahead of time. So I have to plug in the square root of 64 there. I know the square root of 64 is already 8, right? kind of calculating these things in steps usually makes it a little bit easier. Just in terms of like the parentheses and things that you might need once you get to your calculator. But with this kind of exactly what we were doing before, just instead of looking at the z value to find the probability, you're looking at the probability to find the z value. Questions on that? I want to show you this in Excel, but I also think I have something that I want to do first. So, I think I told you this last week. I told you I would show you why, and we didn't get far enough. So, I'll show you why something I was telling you. So, let's think about. I think I told you, and let's see if I can remember the value. I think I said that if we go one standard deviation to the left and the right, to the right of the mean, I said the probability we see something within a standard deviation above or below the mean is 0.683. So we always know that's the case no matter what normally distributed variable we're looking at. So let's think about how maybe we could prove this for ourselves. So if we do it two ways, show you what I think is the kind of the old way, the easier way, and then I'll show you how we could do it using this inverse idea as well. So if I go one standard deviation above and below, no matter what my mean is, what my standard deviation is, what will those z-scores be? On one standard deviation below, z-score of not 0.5, right? So what do z-scores represent? They're the number of standard deviations away from the mean that we are. So if I'm looking at a value that's one standard deviation below the mean, my z-score would just be -1. If I'm one standard deviation above the mean, my z-score would be one standard deviation above. So I'm going to use this. Go to my table. So I go down here, a z-score of -1.00, so 0.1587. So that's the area to the left here. With the probability of seeing something one standard deviation below the mean, or even further, right? I could then look up that z-score of 1.00. I find the area to the left of that is 0.8413. So if I want the probability of seeing something in between one standard deviation above and below, I would take this smaller area, subtract it from the larger area, and I'd be left with just what's in between those two values. So if I go ahead and do that, 0.8413 minus 0.1587, I get what? Anybody want to help me out there? Which I thought it was pretty close. I think I rounded it, but it was that original 0.683 I was telling you. So that didn't come from like some magical rule. It's just that we're looking at these z values. We always know the probability of seeing those z values or something below them will be these specific values. So no matter what normally distributed variable I'm looking at, if I'm going one standard deviation above and below the mean, I always know the probability of seeing something in between those two z-scores of -1 and 1 would be that 0.683 if we round it. Any questions on that? On that idea? So, let's see. I want to do this one. Let's think about it in a slightly different way. And you can do the same thing with the other ones I told you. I think I gave you like the 2 and 3 standard deviations as well. It'd be the same process. You're just, instead your z-scores would be -2 and 2, -3 and 3, and kind of continuing out to even like 6 and. So let's say instead, if I want to think about what I just did in a slightly different way. So I said if I go one standard deviation above and below that mean, the probability of seeing something in between that range is 0.683. So what would the probability of seeing something outside of that be? Just 1 minus that. So I know the total area kind of in these tails here is 1 minus 0.683. So what? 0.317. How much would that be in each tail? This is a symmetric distribution. Yeah, half of it would be in each tail. Right? These are the same size tail. This folds on top of itself. So if I divide that by 2, get what? 0.8. Yeah. So 1/5. Okay, so I know this area is 0.1585. What is Z value would give me 0.1585 in the lower left tail, and then that same Z value, but positive, would give me 0.1585 in that right tail. Well, it should be, what I'm telling you is true, what should the Z value be? 1 and -1. So let's look it up in this table. We've got, I already forgot, what was it? 0.1587. So scroll down here. 0.1587, sure enough, -1.00. Right? So we can actually kind of prove that to ourselves, kind of working in either direction there with that normal distribution. Any questions on that idea? But we don't have to like go through these steps. I'm showing you this more of like to kind of hopefully get a better understanding of what we're doing, right? In practice, we're never going to have to like work through them both directions. It's just helpful to maybe see it kind of work through in both ways. So the other thing I want to do today to end class is take a little bit of a look into Excel. So I'm going to sit down so I can type easier. All right, so we kind of worked with some of this, and you can ignore this for right now, but we worked through some of these norm.s.dist and norm.dist examples last week. I'll kind of work through and show you how we could do the inverse work in Excel as well. So I'm going to go to this inverse transformation worksheet that I have in that Indiana weather data file. And I have the exact example that we just worked through in class with that exam score. So I kind of set this up in a nice way. So for right now, I'm going to delete these 3 values, just to kind of show you how we use these functions. So I've got my mean up here, my variance, and here's that area that I wanted in the left tail, right? So this was like when I wanted to find the bottom 40% cutoff. Or I could do, what was that cutoff for the 90th percentile, right? Or what was the test score that was 90% of test scores below it? Now, that was the first example we worked through. So if I want the probability that X is less than or equal to some cutoff value, and I know that that probability I want is 0.9. So I'm trying to work in reverse. I know the probability, trying to find the X value, right, or the test score that is the cutoff for the 90th percent. So I'll do norm.s, norm.inv. Okay. So if I use this norm.inv function, I then tell Excel, okay, what probability or what cumulative probability do you want the area in that on the left side there? Well, I wanted it to be 0.9, right? That was kind of the example we worked through. Comma, what's the mean? Have the mean up here. And then comma, what's the standard deviation? Well, I've got the variance in a cell here. I could calculate the standard deviation in a different cell if I wanted to and then reference that. Or I could just say, well, I know that the standard deviation is always going to be the square root of the variance. So notice I can use like multiple functions and things in Excel all within the same cell. I don't have to break it down to parts. Now I can, and for you guys as you're learning it, that is often maybe a little more helpful to kind of keep track of your work and identify maybe where you're going wrong or where you have an error. But once you start to get familiar with them, you can put everything in the same cell. So what this will do is it'll take the area that you told it, right, 0.9, go to the table, look up 0.9, find the corresponding z-score, just like we did by hand, then use that z-score, the mean and the standard deviation, plug it into the inverse transformation formula, and spit back out at you what that cutoff value would be to see 0.9 in that left tail. Sure enough, we get, I think ours, we had to do some rounding, so we had like, what, 82.26, I think. Well, here we can get very exact, right? We don't have to do any rounding of our z-scores to the second decimal, or you know, the probability we find is going to be a little bit off of 0.9. We can look up exactly 0.9. Okay, so Excel allows us to be a little bit more precise than doing it by hand using those tables. Now, if you were doing it by hand, you can still be precise if you want to do the integration, but that's, you know, most people don't like to do that every single time they want to find the probability from a normal distribution. Okay. Any questions on that? Okay. So the other way you could do it, right? If we remember, our inverse transformation formula was something like this, right? Take the mean, add the z-score times the standard deviation. So instead of using the norm.inv, just like we had norm.s.dist and norm.dist, we can find first the z-score that would be the cutoff for that probability of 0.9, or that cumulative probability of 0.9, or the area to the left of 0.9, right? All different ways of saying the same thing. Okay? So I can use the norm.s.inv, which says, okay, use a standard normal distribution and just return to me the z-value, or the number of standard deviations away from the mean I need to be to get that probability of 0.9 below that z-value. So I tell it the area that I want to the left from that 0.9. This will give me the z-value. Remember, when we looked it up, we were between 1.28 and 1.29. So we had to use the higher of the two. That's why we got, you know, our answer might be a little bit different than what Excel tells us, because Excel knows it's in between 1.28 and 1.29, but it can find the exact value that it is, right? So 1.28155, okay? So now that we have that z-value, we can use Excel to do a little bit, just basically do the math for us, just like a calculator, right? So I'll take my mean, I'll add that z-value, and I'll multiply that z-value by my standard deviation, which once again, I'm going to do the square root of the variance there. Okay. So two different ways of doing the same thing. Hopefully when I hit enter here, I get the exact same cutoff value, right? Because it's still should be the cutoff value for the 90th percentile, right? Sure enough, get the exact same thing. Okay. So we can always like do the intermediate step, right? Like use the norm.s.inv and then plug it into the formula, just like when we did norm.s.dist, found the probability that we wanted, right? We had to first calculate the z-score to put it into norm.s.dist, or we could just skip it altogether, skip the intermediate steps, use norm.dist, or here, skip all the intermediate steps, just use norm.inv. Any questions on anything that we did there? I want to see something again. You know, and if I have it set up this way, it's kind of nice, because now what if I want to find the bottom 40%? That was the second problem. Well, I've got everything referenced, just updates everything automatically, right? I could find the cutoff score for 50%. What should that be? Find with the score that there's 50% to the left, it should just be the mean. So what's my mean here? 72. Sure enough, right? If I want that probability of 0.5, that cutoff would be that mean of 72. Excuse me. Any other questions on this before I kind of keep moving here? Okay. Where are we at on time? I think, let me make sure that's all I want to say. So I have, you know, some of what we did here. I mean, these are different values, but some of the stuff that we did in the Excel document, just as kind of to remind you the order in which you need to put things in. You can obviously also look at that Indiana weather data file. It has all of the kind of functions in there. You can take a peek at those as well. Like I said, that'll be helpful for that first kind of part of the Excel assignment that I just put up there yesterday. I think that we will talk about sampling on Friday, but today there's one more thing I want to show you. So I would not expect you to do anything like this, but it's kind of an interesting, I guess, exercise, right? And it also kind of shows you the importance of Excel. So I was actually on a panel, I think 2 weeks ago, talking to a lot of freshmen, and I was encouraged to hear there was, I think, 4 other professors, and the advice we all gave, like, what's one thing, a good skill to have, and everyone agreed that Excel or some, level of experience and even a mastery would be great, but you're going to be expected to use this once you kind of get out there. Actually, I had another student come to me a month ago, and he had an internship. I think he's only a junior, but they were wanting him to use like pivot tables and stuff, which is stuff even further outside that we're, further outside this class, but there is that expectation. So that's why I'm really trying to kind of show you what its power is, while still also remembering that although you should know Excel, you don't from previous classes, or at least that's what I've been told. So here what I did was, real
quick, the Excel assignment is the 22nd.
I think it was the 27th. It's on.
27th.
Yeah, the Connect assignment is 22nd. Yeah. So we got quite a bit of time here.
Okay, great.
So if I have this norm.s.dist function, if we think about what I had that z, or that standard normal table, I basically could plug every single z value to the second decimal in and figure out what that probability was. So I could reproduce all those, but I'd have to type that norm.s.dist in, put in 4, then put in -4.1, -4. I'd have to type this out a lot. So if I just want to put it in once and then copy it across and copy it down, right? We actually could use a combination of this if statement, right? To basically and add up kind of the first decimal to whatever that second decimal place is, right? So if I want -3.7, -3.71, -3.72, the problem is when it's negative, I don't actually want to add this second decimal, I want to subtract it. And then when they're positive values, I actually want to take the first decimal and add the second, right? So I had to kind of use this if statement to get around that. Also notice we'll always only freeze the entire cell reference, but there's some tricks where I can actually just freeze the row or just freeze the column. That will be helpful in an example like this, because when I copy this across, I don't want cell A2 to change, but I want kind of the B1 to update to C1 to D1, right? So I can use this combination where I only freeze the row or only freeze the column. I won't expect you to do that in anything we do in this class, but this kind of shows the power is I typed this formula in once here. Once I make sure my logic works out correctly, right, and I can actually delete this and show you, right? I can copy this all the way across, and then I don't even know where it stops, so I probably went too far here. Yeah, we did. I'll delete this, all right? But now I've basically got the probability that's associated with all of these different z-scores, right? So I could build that z table myself in Excel using that norm.s.dist function, right? And if I wanted to make it 3 decimals, right, I would just create like more, I could maybe do more row and column headings. I could do some goofy things where maybe I, do like a couple lines on it, but we can reproduce it. It just kind of shows the power of Excel. I would highly suggest if you ever want to do anything outside of your classes, look at, I think Google has a certificate in Excel, even just kind of going out there, Google searching like Excel tutorials or Excel topics to master. There's a lot of resources out there that would kind of be advantageous to you kind of as you're leaving and thinking about your careers. All right, well, that's my wise sage advice for today. I will see you guys on Friday.